Hello wonderful person, this is Anton and welcome back to Kerbal Space Program and part 7 I think of our attempt to make an autopilot, basically something that will allow us to do everything automatically but by making our own code in Python. Today we're going to be taking a look at this code that will allow us to initiate a moon transfer. This is all we're going to be making today, and if everything goes fine, we're going to propel our craft to the moon and hopefully maybe not miss it. Anyway, welcome to What the Math. Now, what exactly are we going to do today? We're going to initiate what's known as a Hoffman maneuver, and this is something that basically NASA does pretty much every time they send something to Mars or Venus or other planets. The way it works is by doing the following. I'm actually going to help you visualize this. So right now we are in a relatively circular orbit around Kerbal. We're trying to reach this orbit right here, which is the orbit of the moon. The way we're going to do this is by essentially, let's just add a maneuver node here, by blasting our engine for a specific amount of fuel until our new orbit intersects with the orbit of the moon. Now, there's actually a way to calculate exactly how much you need to spend in terms of fuel to reach this point. Now, normally, if this was a Hoffman's maneuver or Hoffman transfer maneuver, as it's more well known, you would then fire your engine here. You would have another node here to then basically circularize your orbit and create a new circle aligned with this orbit. This is kind of how, for example, geostationary satellites transfer to a geostationary orbit. It actually requires a lot of fuel, even more fuel than is required to escape the actual planet. So it's even over the escape velocity of the planet, but this is kind of how it works. We are, however, going to be doing something just really simple. We're going to blast our engines and get the intercept course with the moon, and then essentially just go straight forward and crash land on it. We're not going to be getting into orbit around the moon because it's not really what we're going for here. We just want to land there. Now, normally, if you were to do this manually, you would just kind of like adjust this until you get the intercept with the moon, and you then kind of plan out your intercept really carefully. Now, notice how, even though the moon is there, if I move this here, you don't really get the intercept yet. That's because by the time you get to this part of orbit, the moon will already have moved. So you actually have to move over here for you to get that intercept. Now, this is where all of the calculations come in handy. And this is actually all accessible on Wikipedia. This is exactly where I got all of the formulas for this from, under Hoffman transfer orbit. We are going to be using two formulas here. The first one is for the actual velocity. And I think I used, let me actually just double check what I've used here. This is the delta V calculation. This is the part you get in the script. By the way, this is in the description below under GitHub. So we're using the formula for delta V, which is this formula right here. So basically, to find the actual delta V needed for the actual transfer, you would take the value of mu, which is already given to us in the game, and I've used it previously. It's the so-called standard gravitational parameter. You divide this by R1, which I believe stands for the first orbit. Then you divide it by this and -1, and you'll get the actual value. Now, I'm not going to calculate it just yet, but for the moon, it always gives you pretty much the same value because the moon's orbit is circular. So no matter what part of the orbit I start from, it will be relatively similar because my orbit is also circular. But it will change if you actually have an orbit that's not 100 kilometers like mine. Like, for example, if your orbit is 200 kilometers, then your R here will change, and you'll actually be using something different as well. So all of these values are given to us. R1 is the vessel's semi-major axis, which is found using this command right here, vessel.orbit.semi-major axis. The mu is the gravitational parameter, which is also available using the command right here. And the only thing that we're calculating is the moon's actual orbit. Now, you can actually just take the value from Wikipedia, but I decided to use a formula for this, which is also in the game, by accessing the bodies, which is how you access all of the different planets and different moons in the game. And the reason I wanted to do it this way is because this way you can actually then apply it to any other object. Like, for example, if you wanted to go to Duna, you would just change this to Duna. And that position or orbital frame will give us, let me just show you what it does. It will give us this value right here. Now, this basically shows you the position of the moon around Kerbal. So we need to take these two values and use the Pythagoras theorem to basically calculate the actual distance or the actual semi-major axes. I did it very simply by doing the following. It's right here. It's this little formula right here. It's the square of this plus square of this, and then you add them up and take a square root. In other words, if I just copy paste this and type this into the game here, what you'll get is the value of basically 12 million meters, which is about 12,000 kilometers. You could actually just copy this from Wikipedia or from the game, but I decided to do this via the calculations. So that's really the only thing that I added here. The delta V is calculated using the formula I showed you before, and the only thing that I haven't explained to you is the so-called phase angle. Now, this is really important. And I think one of the better ways of explaining what these phase angles are is by using this chart from this person that has an account with just numbers in his name. He created, or she created, this really cool phase angle chart that shows you when to begin your transfers from Kerbal to other planets. Now, for example, if you want to transfer to Duna, the phase angle has to be, as you can see, 44 degrees. As the Kerbal moves around its orbit, the angle will change because Duna moves a little bit slower. So, in other words, when you reach the point when the angle between them is 44 degrees, that's when you would start your burn. Now, for us, because we're going from our own orbit to the moon, we actually have to calculate this angle. It's not really given to us. And to calculate this, we're going to first calculate the actual phase angle needed. I'm going to show you a formula for this in a second. And then we're going to calculate the current phase angle and when they basically align, when they're relatively equal, which I do right here in this part, basically by running a constant loop and checking if the angle plus the difference between them is more or equal to 0.1. The reason I did this with absolute value and everything is because it was sometimes giving me negative values, so I actually had to make sure that I ignore those signs. And this seems to work just fine. Now I'm going to show you how to find the actual phase angle that's needed first, and it's using this formula right here. Now, where is this coming from? Well, this is actually, once again, from the Wikipedia page on Hoffman transfer orbits. Right here on the bottom, it gives you this angular alignment formula. It does look kind of complicated, but basically it's pi multiplied by 1 minus 1 over 2 root 2. And the only variables we have here are the original semi-major axis divided by the moon's semi-major axis, which is, if you remember correctly, 12 million. So using this, which I'm going to do right now, we can actually find out what is the angle that we need for the transfer. And if I run this, it gives you 1.96-ish. That's in radians. Now that's out of 6.28 or 2 pi radians. So in other words, if I go back to the picture here, when our craft is about 1.95 radians behind the moon, that's when we would start burning our engines, and this is what would give us the perfect orbital alignment. In other words, so where's the moon? Let's find it right here. We have to, so if I were to draw a line going this way to the moon, and to then draw another line going somewhere here, this angle between them has to be about 1.95 radians, which is, according to Google, about 112-ish degrees. Now, we're going to be working in radians though, just because it's more accurate that way. So just to kind of manually test this, so let's just place the maneuver here and place it around, so okay, this is about 112, right? So it's about here somewhere. And look at that, we get the intercept. So that's a pretty accurate calculation. Now, in other words, at this location, which is 1.95 radians if you were to draw a line this way and this way. Okay, that's not exact, it's actually here. If you were to draw a line here and here, there we go. That's about 112 degrees or 1.96 radians, as we just calculated. But we now need to find a way to actually calculate where our craft is as well, because we want to start burning our engine when the moon is at the specific phase angle from us. If I just place my node here, then by the time my craft gets here, you'll see this in a second, by the time my craft gets here, moon will already have moved, so it's still not going to be very accurate. So we need to actually constantly calculate the phase angle and compare it to the angle where the moon is, which is why I have this loop written down that basically constantly calculates both the current phase angle and the angle needed. And when the difference between them is practically non-existent, that's when we start burning the engines. Now there's one thing that I didn't explain to you, and that's how we find the current angle. So that's the angle needed. This is the current angle. If you want a more specific explanation, I'm actually going to point you to the link where I found this. This is a Python's way of calculating the angle between two vectors. And I found this answer right here on Stack Exchange for mathematics. A person was asking a question, how to find an angle in the range of 0 to 360 between two vectors. And the best response was by the person whose name is MVG. He essentially gave us the definition. So there's a dot product we have to find, the determinant, and then by using the so-called a10.2, which is actually a command in Python, you can find it under math a10.2, you can then find the specific angle. So just to kind of give you a brief summary if you didn't really understand what we're going to be doing, we're going to be looking for an angle between two vectors, one formed by the moon and one formed by our craft. And to find this angle, we just need to know this point where the moon is located, this point where our craft is located, and then we find the so-called dot product by using this. We use the determinant formula to find the determinant and plug it into the math.a10.2 function to discover what the angle is. Now we're not actually going to go into more detail than this, but essentially this will just give you an angle, and when this angle equals to the phase angle that we calculate here, that's when we will start firing our engines. I believe the sign is actually going to be negative because it's going to be behind the moon. So for this reason, instead of subtracting them, we're actually adding them up. And the last thing that we're going to do is, well, how long do we actually have to fire our engines in order for us to actually achieve the required delta V and to basically get the intercept with the moon? We've used this in the previous video. This is exactly the same calculation to calculate the actual burn time. All it does is it uses the vessel's mass, it uses the engine's ISP value, specific impulse value, and then calculates the actual burn time required. This will be different for every vessel, so depending on what you're using, it will have different values. And I also decided to just print out some of the values here just so we can see what's happening, and it will check for this every single second. So while this loop is running, it's just checking things, and as soon as the two angles align, as soon as the phase angle equals to the angle needed, the loop stops, the vessel fires its engine, waits for the burn time value, in other words, waits for as long as it needs to while the engines are firing, and then finally stops the engines completely. So this should basically put us on the intercept of the moon. I'm going to just kind of look at where we're located right now, and I think we may have actually missed the, yeah, we definitely missed the area where we should have been firing our engines. And here you can actually just add another function from the previous video where you could warp the actual vessel to this location automatically. I decided not to add this just to make this a little bit shorter in terms of lines. So instead, we're going to do this manually. Now, I think it should be somewhere here. As a matter of fact, I believe one of the ways to tell when you should be firing toward the moon is to see when it actually comes out from the horizon. So I'm going to show you how to kind of eyeball it in a sense. And as soon as we get to this point, we're going to start our script, and then it's actually going to find the precise moment when we need to fire our engines. So let's see if this works, if all of this is successful, and if we can actually find a way to get to the moon without really doing any manual calculations. So here, I'm going to wait until our craft gets to this position. And one of the first things it's going to do is it's going to activate Autopilot and then engage the prograde positioning. It will wait for 10 seconds because it will probably take about 10 seconds to align, and then start the loop. The only thing we have here are these two values. This is because I actually had to assign the variables to both angle and angle difference before starting this loop. Otherwise, it's actually going to give me an error. So here, let's just position our craft maybe. Actually, I can just totally stop this. We don't need to do this. And what we're going to do is just wait for the moon to come out from the horizon. I might have to accelerate time a little bit. And as soon as we see the moon, as soon as it appears from behind there, that's when we should probably start the actual script. And there it is. Here comes the moon. So that means I can go into the script now and basically activate this. So now it's running. You'll see that the craft will start turning toward the prograde by itself. And right here on the bottom, we're going to start seeing, oh, there we go. It already started. So I was basically practically there. It started firing almost right away because it actually was at the position where it should have been firing already. And it's going to fire for exactly the needed amount. And here it's actually doing the burn time based on the burn time formula from here, from this part, and it will stop right as soon as the burn time is, there we go. As soon as the burn time is out, it stops the, everything. And basically now, if I look at my map, I should be on the intercept with the moon. Now, it's kind of hard to tell, but from this angle right here, you can kind of tell that I'm actually landing on the moon. So this is not the best maneuver, and that's probably because I actually fired my engines a little bit too late. I'm going to try this again just to show you how consistent this is. We're going to actually restart the simulation from my previous save. And so here, what I'm going to do is I'm going to actually start running the script right away. And you'll see that it will actually start producing two values. One of them is this, which is the difference between the angle needed and the phase angle currently. And I also decided to add some text here just so you can actually see what we're printing out. So let's start this again. And it's going to start printing this every second, starting after it aligns the craft. So now everything's aligned, it's toward prograde. And you'll start getting, there we go, angle difference. This is the current angle difference, the phase angle difference between the craft and the moon. And as you can see, it's actually increasing. Then we have burn time, which is 25.65 seconds. And lastly, the current angle of the craft, which is also increasing. So we don't really need to show these actually. So for this reason, I'm going to stop this, mostly because it's going to kind of create a lot of lines here that I don't want to see right now. And let's wait until the craft is almost in the position again, just so I can show you what it does right before it starts firing the engine. So right around now, let me just double check that everything is set. Right around now, it's going to, yeah, there we go. So the angle difference is now decreasing. It's at 0.36. And as soon as it gets to 0.1, this is when it's going to start firing the engine. And let's actually just do the angle difference instead. So right now, I'm going to run this again. And we should be, okay, you don't really see the craft because it's really dark, but we should be seeing only the angle difference. It's going to be very, very precise, very accurate. And there we go, 0.21, and looks like it's decreasing. So remember, when it gets to 0.1, that's when the engine starts firing. So right now, basically what's happening is we have a phase angle that we're looking for, and the phase angle between the moon and the craft is slowly decreasing because moon is moving, but craft is moving a little bit faster. So it's kind of like the minute clock and the hour clock on an actual watch. And so as soon as this gets to 0.1, that's when the engine will engage. You can kind of see the moon is coming out from the horizon right now. The engine will engage and it will then basically fire right around now. And it will use the burn time value of 25.6 seconds. Then it will stop, and hopefully this will put us on the intercept with the moon. So second test, and let's see what we get here. And the engine stopped firing. Let's open the map and look at that. Perfect intercept. We're basically landing on the moon. So I'm going to stop this here. You can check out the script in the description below. And in the next video, we're going to finish this by landing on the moon. That's going to be the last part for this particular series. And we might come back to this later on and do a few more scripts with transfer to other planets and take off from other planets as well. And just to basically automate pretty much everything using Python. Anyway, thank you for watching. Hopefully you enjoyed this miniature tutorial and learned something from it. And do consider using KRPC because it's actually a really good learning tool. Also, subscribe if you still haven't. Share this video with someone who enjoys watching space videos and wants to learn into video games. Let's go to the moon, and I'll see you guys in the last part where we're going to be landing there as well. If you have any questions, post them in the comments below, and hopefully I'll get to answer them. Space out, and as always, bye-bye.